about that.
All right, we're going to see how they're putting this technology to work. Thank you, Fred. I'm here now with Ken Fernandez from the Science and Mission Systems Office. And Ken, you've got a surface mobility operation here that looks like you're just playing with toy cars to
Right.
me.
What we're doing is we're working on technologies that will be needed to field the next generation of surface mobility systems. These systems go beyond what we did in Apollo, which was a system, the lunar rover was a system that just ferried astronauts around. The systems in the future will have to work with a higher degree of autonomy. To do that on Earth is easy, because we have GPS, we have communication satellites, but on a place like the Moon, none of that is present. So we're working on one technology here that we're actually going to demonstrate in the September-October time frame near Building 4614. This is a system that provides both navigational information and communications for a rover. Okay. And for any system. It could work with a lander also. But we deploy these around, and the system works just like GPS, and it's far less costly than trying to implement that on the Moon.
So you deploy those around, and then you send these.
Yeah, and this is a system that we're adapting for NASA use. It's originally a military robot that they use to examine IEDs in the war areas, and we're going to develop computer control for this so that we can operate it autonomously, and we're going to mount one of the navigation sensors that is associated with this and do the autonomous navigation. Other technologies that we're working on are, various trailering operations. One of the things you might want to do with a rover is to go out and find a payload, a nuclear reactor, hook up to it and move it to a safe location without exposing the crew. So this is the mechanisms are an important part. We're also working on various sensors. This is a SICK LiDAR. We're also looking at flash LiDARs. We're looking at neural nets and various autonomous algorithms for providing guidance.
And then the Big Daddy over here.
The Big Daddy is an iRobot R-Gator, and we're using a system that was developed for the military, and because systems like this are available, it saves us a lot of money in developing a test bed capability. So this is a larger platform that allows us to put more sensors on and a lot more capabilities. The little MarkBot over there is great, but it's very limited, but it provides us an initial first cut.
So this is really going to get us to the Moon and see what's there before we get there, right?
Well, hopefully, and it'll help us do a lot of things that we couldn't do otherwise.
All right. Thanks, Ken, so much for showing us your technology.
Thanks, Lori, for coming by.
Sure.
We're here with Jim Richard, who is the team lead of the Valve Actuators and Ducts branch. And Jim, before we get to some of the new technology you've been developing, what is this large hunk of hardware you've got here?
This is the pre-valve, LOX pre-valve for the Saturn S4B rocket. We've borrowed this from the Space and Rocket Center and are using it to evaluate new technologies against for this Ares vehicle.
So you pulled this right out of the Saturn rocket?
That is correct.
How much does that weigh?
This valve weighs about 40 pounds as currently configured.
Well, we'll let you set that down then, since it's pretty heavy. And you can show us some of the new technology you're working on here.
Sure. The upper part of this valve is a pneumatic actuator with a large spring return system in it. And this part of the valve contributes about half the weight of the valve. The new technologies we're working on are Paizo systems such as these. This Paizo system weighs about 4 pounds, and we can substantially reduce the weight of this valve and increase its reliability in the process.
Well, that would definitely be a good thing. So show us, though, a little bit about what you're working on now with the valve section of this.
Okay. This valve has a large disc that's in the flow path, and that causes flow perturbations to the engine. We're evaluating that using new CFD analysis tools to evaluate how to better design that disc for the new vehicle and give better engine performance.
Great. Thanks very much, Jim. We're here now with Michelle Monk. She is the Aerocapture lead engineer here at Marshall. And Michelle, I find it interesting that at a center that concentrates so hard on propulsion, you're actually working on stopping spacecraft, not making them go.
That's right. We're actually propellantless propulsion. When a spacecraft is approaching a planet, it needs to slow down to get into a science orbit. And so you can either do that with very expensive, heavy fuel, or you can use the atmosphere to slow you down. And so that's what we do. We take one pass through the atmosphere and we use the drag to slow our vehicle down and put it directly into its science orbit.
And that's where this very large heat shield comes into play. Tell us a little bit about this.
This is a 2-meter diameter carbon composite heat shield made by Lockheed Martin, and it's a manufacturing demonstration of making a heat shield of this size in one piece.
And this isn't made of metal, so this makes it much lighter, right?
Right. This is a carbon composite, and this system is about 40% lighter than the Genesis sample return capsule system.
Also, it means you can put more science inside.
That's right.
Well, let's take a look at one of the prototypes you have over here. Can you tell us a little bit about this?
We've been doing about 4 years of technology development on the ground, led by Marshall, and we've done lots of material testing and guidance algorithm development and simulation, and now we're proposing to do a validation of the Aerocapture maneuver at Earth, and this is a full-scale prototype vehicle that we would use to do that. And if selected, Marshall will supply the flight heat shield and the back shell for that space vehicle, and JPL will supply the spacecraft for that, and we'll fly in 2010.
In 2010, not too far away.
That's right.
Well, Michelle, thanks very much for showing us your technology here today, and
Thank
we look
you.
forward to seeing it fly.
Thanks.
Hey, Bill, look at all this cool stuff I got.
Well, I guess it has been a neat day here at the Research and Technology Expo.
Yeah, it has, but it's also been interesting to find out how someone has an idea and then turns that into hardware and technology that may take us back to the moon and even to Mars someday.
That's right, and all of it designed or developed right here at Marshall. Well, that'll do it for us. Join us next time as we focus on Marshall.